All right, so today we are taking a deep dive into something that is like, it's all around us, right? Powers a ton of our tech,
Yeah.
but I feel like it's often kind of a mystery,
Mm-hmm.
transistor amplifiers.
Yeah.
So you might be listening to this, getting ready for a class or working on a project.
Right.
Or maybe you're just curious about how these tiny little components
Yeah.
can really crank up the volume,
For sure.
pun intended.
Yeah.
But today we're going to be focusing on BJTs
Okay.
and MOSFETs.
Right.
Those are like the rock stars of the transistor amplifier world.
Yeah. And what's fascinating about them is that they have such different control mechanisms, even though they both achieve amplification in the end.
Yeah, I mean, the acronyms alone are enough to make your head spin.
Yeah.
But I was actually reading about something surprisingly simple, and I wanted to ask you about this.
Okay.
Using a potentiometer to measure an amplifier's impedance.
Okay.
Like those little knobs we use for volume control.
Right.
Is that for real?
It is. It is. You can think of it as finding the perfect balance point. So you swap out the load resistor with the potentiometer,
Okay.
and you tweak it until the output voltage drops by half.
Mm-hmm.
And at that point, the potentiometer's resistance matches the amplifier's output impedance.
Huh.
Yeah, it's an ingenious use of a very basic circuit principle.
So it's not just about controlling volume. It's like this hidden superpower of the potentiometer.
It is.
But why is knowing impedance so crucial?
Yeah.
It's not just a random spec on the data sheet.
Oh, not at all.
Right.
So imagine you're trying to connect a powerful amplifier to a delicate speaker.
Okay.
If those impedances are mismatched, you get reflections, you get signal loss.
Mm-hmm.
It's like trying to force a square peg into a round hole.
Right.
The sound is going to be distorted, weak, and just plain bad.
Makes sense.
Yeah, impedance matching ensures that that signal flows smoothly between stages.
Okay, now that makes sense.
Yeah.
Like you wouldn't want a fire hose blasting water into a tiny teacup.
Exactly.
Okay, so we've tackled impedance.
Right.
But what about the transistors themselves?
Okay.
I always get BJTs and MOSFETs mixed up.
Yeah.
Can you break it down for me in simpler terms?
So think of a BJT,
Okay.
like a valve in a complex plumbing system.
Okay.
A small change in current at the base controls a much larger flow through the collector and emitter.
Okay.
So it's current controlling current.
Gotcha.
A MOSFET, on the other hand, is like a sliding door.
Okay.
The voltage that you apply at the gate controls how wide that door opens, dictating how much current can flow.
So voltage controls current.
Exactly.
Okay, so BJT is like hands-on with current.
Yeah.
While MOSFET is more about finesse using voltage.
Right, exactly.
Got it.
Yeah.
But how do you make sure these transistors are actually amplifying?
Yeah.
They can't just be like chilling on the circuit board.
No, they need to be biased.
Go ahead.
They need to be in specific operating regions. For BJTs, it's what we call forward active mode. And this is where a small change at the base creates a big change in collector current.
Yeah.
Imagine like a sensitive trigger that sets off a chain reaction.
Okay.
With MOSFETs, it's the saturation region. And here, the channel is wide open, letting lots of current flow through.
So it's like you're setting the stage for the main act,
Right.
making sure the transistor is
Exactly.
primed and ready to amplify.
For sure.
And this brings us to configurations, right?
Okay.
I've heard there's more than one way to connect these transistors in a circuit.
Absolutely. There's a bunch of different amplifier configurations,
Oh, wow.
each with their own perks and trade-offs.
Okay.
Let's focus on two common ones for BJTs.
Okay.
Common emitter and common collector,
Okay.
which is also known as an emitter follower.
Emitter follower. It sounds like
Yeah.
a shy sidekick.
Yeah, it kind of does.
But seriously,
Yeah.
how do you choose the right configuration?
So imagine you're trying to amplify a super weak signal from a microphone. You need high gain, right?
Yeah.
That's where the common emitter configuration shines. It's
Yeah.
like adding a megaphone to your voice.
Gotcha.
But what if you're connecting to a delicate sensor
Okay.
that can't handle a strong signal?
Yeah, wouldn't that overload it?
Exactly.
Yeah.
That's where the emitter follower comes in.
Okay.
It offers high input impedance and low output impedance. It's like gently passing a fragile object without crushing it.
Right.
Ensures smooth signal transfer without disturbing the source.
Okay, so common emitter is for boosting weak signals.
Right.
While emitter follower is like a careful handshake with a delicate device.
Exactly.
It's all about using the right tool for the job.
Exactly.
And what if a single stage of amplification isn't enough?
Okay.
Do you just stack up more transistors?
You got it.
Really?
It's like a relay race.
Okay.
Each stage amplifies the signal, passes it on to the next. This creates what we call a multi-stage amplifier.
Okay.
Where the overall gain is the product of the individual stage gains.
So it's multiplicative.
It is.
Which can lead to some seriously powerful amplification.
Absolutely.
So if each stage boosts the signal tenfold,
right,
and you have 3 stages, you're looking at 1,000-fold increase.
That's right.
Wow. But what happens if you push things too far?
Okay.
I'm picturing an amplifier cranked to 11.
Right.
And the sound is all distorted and clipped.
Ah, yes, the dreaded clipping.
Yeah.
So that's a sign that the signal is exceeding the limits of what the amplifier can handle. Think of a swing set.
Okay.
If you swing too high, you hit the frame.
Yeah.
Clipping occurs when the signal tries to go beyond the rails set by the transistor's operating point.
Okay.
And that results in a distorted output.
So it's not just about making things louder, it's about staying within that sweet spot.
Exactly.
Where the signal is amplified cleanly.
That's right.
Now, you mentioned operating point.
Yeah.
And this might be a bit technical.
Okay.
But can you explain those mysterious load lines I keep hearing about?
Sure.
What's the difference between DC and AC?
So they're both graphical representations, but from different angles.
Okay.
The DC load line shows the steady-state relationship between voltage and current for the transistor. Think of it as the baseline.
Gotcha.
The AC load line shows how the signal swings around that DC point.
Okay.
Remember our potentiometer friend?
Yeah.
It can actually change the effective resistance for the AC signal.
Oh, wow.
Which influences how much it can swing.
Wait, so the humble volume knob is manipulating the very lines that govern how the signal behaves.
It is, yeah.
That's pretty cool.
It is, it is.
But there's another component I'm curious about.
Okay.
The emitter bypass capacitor.
Okay.
What happens if you remove it from a common emitter amplifier?
So it might seem small, but it plays a crucial role.
Really?
Yeah, that capacitor,
Okay.
usually labeled CE, acts like a detour for the AC signal, bypassing the emitter resistor. It's like taking the express lane, which leads to higher gain.
So it's boosting the signal even further.
It is.
But is there a catch?
There can be.
Okay.
While bypassing the resistor increases gain, it can also impact linearity, potentially introducing distortion.
So it's a trade-off.
It is.
Between gain and clarity.
Yeah, it's like taking a shortcut through a bumpy field. You know, you might get there faster, but the ride might not be so smooth.
Right. Again, choosing the right tool for the job.
For sure.
This is all starting to make sense now.
Good, good.
We've gone from basic impedance to configurations, gain, and even those sneaky capacitors. It's like piecing together a puzzle.
It is.
And we're just getting started.
My God.
There's a lot more to uncover about these tiny yet powerful devices.
Absolutely. Yeah, it really is like a whole world inside these tiny little transistors.
Right.
But to really understand them, we need to go beyond just those basic connections. Have you ever heard of curve tracers?
Curve tracers.
They're like X-ray vision for transistors.
Oh, wow.
So they show you the relationship between current and voltage in a transistor. Imagine a graph, like a fingerprint, unique to that specific transistor.
Interesting.
Revealing how it behaves under different conditions.
So it can tell you, like, all of its...
It can tell you the operating region.
Okay.
The ideal bias point for maximum output. Even whether it's a BJT or a FET, all just from the shape of those curves.
So it's like a decoder ring for transistors.
It is.
Helping you unlock their secrets.
Yeah.
That's amazing.
It is a very cool tool.
But speaking of mysteries, what about the Miller effect?
Okay.
I've heard it can be a real buzzkill for a high-frequency amplifier.
Ah, yes, the Miller effect.
Yeah.
Think of it like trying to ride a bike uphill with a heavy backpack.
Okay.
It's all about capacitance, which can act like that heavy load, slowing down the signal's response.
Right.
Especially at high frequencies.
So the faster the signal is trying to change,
right,
the harder it is to kind of push it through.
Yeah.
Because of those pesky capacitances.
Exactly.
Is that why high-frequency amplifiers need special care and attention?
Yeah, they do.
Okay.
The Miller effect can limit the amplifier's bandwidth.
Okay.
Making it sluggish at those high frequencies. For a radio receiver trying to pick up a weak signal. That's a big problem.
Yeah.
You need that clear, fast response to capture all the details.
So, okay, this is interesting.
Yeah.
So you're saying that even though that emitter bypass capacitor boosts gain,
Right.
removing it might actually help with high frequencies because it reduces the capacitance.
That's right.
It's like taking off that heavy backpack to climb the hill faster.
Exactly. You're catching on quick.
Thanks.
It's all about balancing those trade-offs, right?
Right.
Do you want more gain
Yeah.
or do you want a wider range of frequencies? It depends on the application.
Right.
Sometimes you need a specialist. Yeah.
Sometimes
Sometimes you need a jack of all trades.
That makes sense.
Yeah.
This is making me think about differential amplifiers.
Okay.
I know they're really popular in audio circuits,
Yeah.
but how do they actually work?
Yeah.
So they like two amplifiers battling it out?
More like two amplifiers working in perfect harmony.
Okay.
Imagine a seesaw.
Okay.
Differential amplifiers have two inputs, and they focus on the difference between those two inputs.
Okay.
Any signal that's common to both inputs gets rejected.
Interesting.
So, like, keeping that seesaw balance.
So it's like having a noise filter built right in.
Exactly.
No wonder they're used in audio where you want a clean signal.
That's right.
But how do they pull off this magic trick?
Symmetry is key.
Okay.
They use two matched transistors in a configuration that amplifies the voltage difference between their bases while rejecting any common voltage. So one side goes up, the other goes down. It's that push and pull that gets amplified.
Okay, so they're essentially amplifying the contrast between the inputs.
Exactly.
That's clever.
Yeah.
And how do you adjust the gain in a differential amplifier?
So
Is it like fine-tuning the balance of that seesaw?
you got it.
Really?
The gain is mainly set by the ratio of the collector resistor to the emitter resistor. Change that ratio, and you change the leverage of the amplifier.
Oh.
But even these sophisticated amplifiers aren't immune to the Miller effect.
Oh, no.
Those pesky capacitances can still limit their bandwidth at high frequencies.
So even with two transistors working together,
Right.
those high frequencies can still be a challenge.
Yeah.
But I'm sure clever engineers have found ways to tackle that, right?
Of course, careful design and compensation techniques can help extend their bandwidth.
Okay.
Keep those high frequencies in check.
So it's all about outsmarting those pesky capacitances.
It is, yeah.
Then we've covered so much ground already.
We have.
It's amazing how much depth there is to these tiny components. From basic configurations to curve tracers and the Miller effect.
Yeah.
It's like a whole ecosystem of electrical concepts.
It is, and each concept builds on the previous one.
Yeah.
Like layers of a cake. But we're not done yet.
Oh.
There's still more to explore about getting the most out of these powerful little devices.
Yeah, it really is mind-blowing how these tiny components are like the foundation for so much of our technology.
It is, yeah.
But let's get down to brass tacks.
Okay.
What about troubleshooting?
Right.
You talked about clipping.
Yeah.
But what are some other common problems you might encounter when you're building or working with amplifiers?
So imagine you've built your amplifier, you flip the switch, and nothing.
Oh, yeah.
Silence. That's a pretty common issue.
Yeah.
And it could be caused by a bunch of things. Maybe a transistor has given up the ghost, or there's a break in the biasing network. Right.
Or perhaps a capacitor decided to short circuit.
So it's like a detective mystery, right?
It is.
Hunting down the culprit.
Yeah.
In a sea of components.
For sure.
Where do you even begin?
Well, your trusty multimeter is the first tool you reach for.
Right.
It's like a doctor's stethoscope for your circuit.
Okay.
It helps you check for continuity, measure voltages across components,
Yeah.
even test the transistor itself.
So is there a signal where there should be?
Exactly.
Is the component getting the voltage it needs?
That's right.
So it's about systematically going through the circuit, looking for clues, eliminating suspects.
Absolutely.
And of course, don't forget the power of observation, right?
Right.
A burnt resistor or a loose connection can sometimes be spotted with just a quick visual check.
Absolutely. A keen eye can save you a lot of headaches.
For sure.
And having a clear schematic diagram is like having a map of the territory.
Okay.
Tracing that signal path.
Yeah. And understanding how everything's connected can help you really pinpoint that trouble spot.
It's like connecting the dots, right?
It is.
Sometimes you just need to step back.
Yeah.
Look at the bigger picture and think about how the different pieces of the puzzle fit together.
For sure.
And maybe take a break, grab a coffee, and come back with fresh eyes.
Sometimes that's the best approach.
Yeah, sometimes that's all you need.
Right.
Well, it feels like we've been on this like epic quest
We have.
Through the world of transistor amplifiers,
Yeah.
we started with those basic building blocks, BJTs and MOSFETs,
Right.
explored their different personalities and configurations,
Yeah.
grappled with gain and impedance.
For sure.
Even faced down the mighty Miller effect.
Absolutely. We covered a lot of ground.
And we even learned how those simple potentiometers can reveal hidden secrets.
They can.
How curve tracers are like X-ray vision for transistors, and how to tackle those frustrating troubleshooting moments.
Yeah, it's all about understanding the tools and the techniques.
It's amazing to think that it all started with this simple desire to control the flow of electrons. Now we're talking about shaping signals, amplifying sounds, building the backbone of modern technology.
It is pretty remarkable.
It's like having a superpower.
It is.
And the best part is, this is just the beginning.
It is, yeah.
There's a whole universe of possibilities out there just waiting to be explored.
Absolutely.
So as we wrap up this deep dive, we leave you with a challenge.
All right.
Now that you've gotten this glimpse of what's possible,
yeah.
What will you create? What signals will you amplify?
Right.
What problems will you solve using this newfound knowledge?
Good questions.
The only limit is your imagination.
That's right.
Go forth and amplify.
I love it.